All right, well, thank you so much for the invitation. In this last talk of the conference, I'm going to sort of entertain you with something very, very simple. I want to take us back some years ago. In 2007, we got in our group the very first sample of diamond with a high concentration of nitrogen vacancy centers, and I already had a laser pointer like this, and this was on a napkin, and you shine the laser on it, and you see kind of reddish fluorescence, and of course we know that what we see is photoluminescence with ZPL, zero phonon line and phonon sideband, and there is a Stokes shift from green to red, and you also can see NV minus and NV zero. So this was a very simple experiment to do, just look by eye. And in that spirit, I would like to tell you about some magnetometry that's about at the same level of complexity as that experiment, maybe a little, just slightly more complex. Of course, yeah, so this is the, I don't need to introduce this audience to what NV centers are and what Stokes shifts are. And just want to maybe make one comment that NV centers, they are deceptively like atoms. They have a simple energy level diagram, but they are not really an atom. An obvious thing, every atom is the same, and every NV center is not the same. And there are all kinds of subtleties that come about because of that. Nevertheless, even with NV centers, you can do moderately fancy things like electromagnetically induced transparency based all-optical magnetometry. Unfortunately, only at low temperatures this has been achieved so far. So this is the energy level diagram once again, which we will try to skip. Okay, so primitive magnetometry based on nitrogen vacancy centers. We go back to my original experiment, and the only thing we need to do here is to bring a magnet. So you take a magnet and you just start waving it around this. And indeed, looking by eye, you see that the brightness of the photoluminescence changes. Okay, so now you can do an experiment which is a slightly more complex version of that. So you align your magnetic field along one of the nitrogen vacancy axis, and you actually don't look by eye, but with a photodetector. Nevertheless, when you do this and you plot photoluminescence as a function of magnetic field, so you see that there is some dependence. This is at the level of a few percent, 5% maybe, a broad feature near zero, and then a number of sharper features. And it's an interesting question of what these features are, and basically they are all related to some kind of cross-relaxation between different subsystems. For example, it could be just, well, you can say cross-relaxation or maybe mixing of sublevels by transverse field. These are not unrelated phenomena. There are things happening at near zero field and at this particular value of nearly 600 Gauss, that little thing. And then there's also cross-relaxation, for example, with substitutional nitrogen or P1 centers, and this gives a bunch of features here that are quite sharp. And then there is a very pronounced feature here, which is the ground state level anti-crossing, where the m equal to -1 level comes close to m equal to 0 level. And, you know, I've been in the magnetometry business for a couple of years, and whenever I see that a signal depends sharply on magnetic field, I say, let's do magnetometry, right? And in fact, if you look at this this offers a nice possibility of doing magnetometry without microwaves. You just need to tune in the vicinity of one of these sharp lines, and there you have your magnetometer. Why would you do this? And in particular, so we are interested in the near zero features, and I call this primitive magnetometry. I already heard this already at this meeting also. So there are many motivations for doing this. One motivation, and I'll tell you about the whole serious program that is going on at the moment, that basically now it says, I'm very pleased to see this as a slogan in the field, that cells don't like to be microwaved, you know. So, and when you do NV center sort of traditional optically detected magnetic resonance, you have to apply microwaves. Also, superconductors don't like to be microwaved as well, or maybe they like, but they stop being superconductor. Sometimes you need to measure at zero fields also in the context of measuring either biomagnetic fields, fields from the brain, for example, or when you're doing fundamental physics, measuring things like electric dipole moments of atoms, molecules, and the neutron. And also, I find the idea that making very simple devices is also good, so reducing complexity and price. So here is another version, a little bit more detailed version of the same plot. This is photoluminescence as a function of the magnetic field with all kinds of features. And when we actually started looking at this at low temperatures, we were completely surprised to see this kind of behavior with a total loss of contrast. And we remained puzzled until Patrick Miletinsky beautifully explained everything to us what is going on. This has to do with the processes in the excited state of the NV center. The reason I'm showing you this is that in addition to this broad feature near zero, there is also a sharp feature. It's not super pronounced, but it's there. And we want to point our attention to that feature over there. And I must say, I'm going obviously to talk about our work, but there was beautiful work done by Clement, was also presented here, and I must say I was very happy to be on this guy's PhD committee because it was a very enjoyable experience. And his advisor, Gabriel Hetet, they did very beautiful work in that direction as well. All right, so long story short, you go to zero field and you also see these features over there. The denser the NV sample, the more contrast you have, but also the broader the feature is. And for magnetometry, you can think that there's some sort of a figure of merit. You can go sophisticated, but you can also go primitive in the spirit of this whole approach. And basically, you want a bigger contrast and a smaller line width, so you can take the ratio and say, this is my figure of merit. Here is some measurement from our lab. And here you see the contrast as a function of concentration, and then the width as a function of concentration, and then our primitive figure of merit. And now you can see that it's no longer completely obvious what kind of diamond you want to take to work with these features. We were looking at things like effective laser polarization, transverse field. It's still in progress on pump light color. At first, we were really puzzled not to see any of this feature in layered samples. Now, I think this is no longer the case. So there's an additional study going on together with, I'm sorry, I'm not done. So, how it's going forward instead of going back. Yes. We have an ongoing project with collaborators at Leipzig who are preparing sort of custom layers with different concentration, different properties to study this systematically. So this work from our group is available on the archive. The main driver is Omkar, who is here, who also presented this in his poster. And this is Teal. He used to be our senior PhD student. Unfortunately, we just lost him to industry. We didn't lose him, thankfully, but lost him for industry, yeah. And so maybe you have seen in Omkar's poster that if you apply some bias field and then you start rotating the diamond, then you see these beautiful patterns that are emerging. And I always have trouble to remember which one is simulation and which one is experiment. Actually, this one is simulation, this one is experiment, because they agree so well. And these features can be used to do sort of vector magnetometry, microwave-free, or maybe almost all optical. We have a debate with ongoing debate with Patrick about what is all optical and what is not. Some interesting direction now is that we're looking at nanodiamonds, where there are many interesting applications, like biosensor and rotation sensor, potentially at the level of one biological molecule, or maybe organelle or something like this. That's yes, and this actually brings me now to telling you a little bit about more what kind of applications this simple thing might have. And I'll tell you about a number of applications, and I've just a disclaimer that the zero field features are not yet used in all of them, but we are thinking about using them in all of these applications. And one of the interesting things that we have at Mainz, of course, is that we have a very beautiful condensed matter group, and they study all kinds of things like magnetic domains and skyrmions. And so a few years back, we got together with them and made a combined MOC, magneto-optical Kerr effect, and magnetic imaging system with NV centers. And so you might say, well, they're both measuring magnetic properties. Why would you have these two things in one and the same system? And this is something that was mentioned by one of the previous speakers. If you actually take a magnetized sheet, uniformly magnetized sheet, and magnetize it in any direction, there is no stray field at all. And the only reason objects like this, like refrigerator magnets, actually stick to the refrigerators because they are actually Halbach array. And if you never done this, I invite you to take two refrigerator magnets and play with them. So put them the refrigerator side towards each other and move in one direction and the other direction. You will find that they are periodically poled, and then turn them around, and oh magic, they don't interact. It's a one-sided magnet, actually, okay? So, but this example shows you that even though you can have full magnetization measured by magneto-optical Kerr effect, you would see no stray field. So there is no degeneracy between these two measurements that are complementary to each other. And in fact, this is the image done with this combined system. This is actually well, it's maybe not a skyrmion necessarily. This is actually a magnetic domain thing, and as you change, is it moving? Yes. Then you see there is some life on the sample happening. And this is this was published a couple of years ago, and this is again a nitrogen vacancy-based system, and it would be nice to get rid of microwaves in it, and that's one possible application. So here is another slide illustrating superposition of the MOC and the signals. So our group is really interested in this unusual kind of nuclear magnetic resonance, which we call ZULF NMR, which is zero to ultra-low field NMR. And so there is high field NMR, there is low field NMR, like Earth field, for example, or something like this. So what we are interested in, lower than low, okay? Basically, Earth field is a terrible thing for us, so we actually, instead of superconducting magnets, we have magnetic shielding. And the idea for this whole field, so this is the conventional NMR, and like many other things that consists of 3 parts, NMR also consists of 3 parts. It's polarization, excitation, and detection. Quantum computer, you know, is initialization, operation, and readout, and these are the same thing. Everything consists of 3. So the idea of this Zulf NMR is that we get rid of the need for strong magnetic fields in each of these stages by doing something smart. For example, parahydrogen-induced polarization, or this photo DNP, dynamical nuclear polarization, which is a beautiful thing. You take a sample, special sample, and then you shine light on it, and it becomes nuclear polarized. That's all. That's beautiful. Hyperpolarized. So 5 orders of magnitude higher polarization than you get from thermal polarization, for example. Then we base encoding on spin-spin couplings rather than chemical shift. And then we do use non-inductive readout, for instance, atomic magnetometers or NV centers. And this way, now we have the entire NMR process, and it doesn't require any high fields. And you might say it's science fiction, but it actually works. This is a recent paper here from last year that shows actually biologically relevant molecules that are detected in a portable system based on this zero field NMR. Another application is measuring superconductors, and here we had very productive collaboration with a number of people, some of whom you may recognize here. Indeed, we were able to measure vortices in high TC superconductors and study them. And microwaves was always a concern, how to not heat the sample, etc. And so going to these microwave-free features is extremely interesting for this. And maybe even nanodiamonds, because maybe one day an experiment can be done. You have your superconductor, and then you have salt and pepper, and instead of that you have nanodiamonds. So you go, and then you just look at this and you see your vortices, right? Wouldn't that be nice? We're working towards that. Right. Of course, this is well motivated because people for many years have been predicting the phenomenon of island superconductivity, which says that way before, well, as you cool a superconducting sample, then way before you see superconductivity in transport, when your resistance goes down, there should be topologically disconnected patches that are already superconducting, and you cannot see them. You cannot see them in transport, but you can see them by the Meissner effect. And there's a whole class of these compounds called underdoped superconductors, where people are very interested in studying this kind of phenomena for obvious reasons. There's also a dream of actually doing diamond superconductivity in this context at some point as well. And if you are interested in this, actually, together with Patrick and other folks, we have already, oh man, it's getting old. It's already 5 years ago we wrote a little review, but maybe still useful. All right, another application is rotation sensing based on NV centers in diamond. You can do electronic gyroscope, but that's not really competitive. So in the end, you want to do nuclear NMR gyro. And there were several papers, including ours, proposing this in 2012. And it took about 10 years until this was actually realized. Well, OK, 9. And it is working. This is now based on the nuclear spin of the nitrogen intrinsic to the NV centers. But eventually, this is moving in the direction of using carbon-13 in diamond for even higher sensitivity. So there are also a lot of biological applications. For instance, we have an ongoing collaboration with people in the clinic, in a university clinic, in Mainz, and they do mind control. And mind control works like this. So you can control your mind by cutting out the head, putting electrodes, and applying the electric field. But as my student says, it hurts, right? So instead of doing that, what you can do is remember Mr. Faraday, who said that if you apply, pulse magnetic fields, they induce electric fields, and with that you can also control your mind. And this is the scientific term for this is called transcranial magnetic stimulation. And this is a well-established technique. So, for instance, you can, the reason you have a hand here, so our colleagues, they know a particular way they line these coils outside of the head. They press the button, and the patient goes, whoop, and moves the finger, and they try to resist, but very hard to resist. Maybe not impossible, very hard to resist this sort of mind control. And so we decided, there's a whole industry of people trying to put magnetometers next to the TMS excitation. But it's hard. There is a huge, 1.5 Tesla in some faster than a millisecond. There's a huge pulse that very hard to put magnetic sensor there. So we decided we're not going to do a hard thing. We're going to do a much easier thing. We decided to study the propagation of nerve pulses through the hand. And the hand can be shielded separately, right? So this is actually a commercial magnetic shield. All we need to do is pop the lid off and put the hand in, and then put an array of magnetic sensors down there. And yes, so this is we use for this particular work, we actually use the atomic magnetometers, and this is one of our incognito patients. Whom you may recognize him actually if you look very hard. But anyway, there is the magnetic shield, and what he was wearing on his head is the normal electroencephalography system, which maps the electrical signals in the brain. And so these are the magnetic signals on different sensors here as a function of time, and you can actually do a simultaneous map of what's going on in the head and what's going in this peripheral nerve pulse, and then you can correlate this thing. Another application is trying to measure magnetic fields from plants. So biomagnetism is a hot thing. People measure heart, measure brain. Plants, everything is very slow, and so the currents. There's an American expression, watching the grass grow, or maybe English. I don't. So meaning something happening very slow. So the currents are low. You expect small magnetic field. So our idea in trying to extend biomagnetism to plants was to find some plants where something fast is happening. And one of the things we tried is a Venus flytrap. This is a carnivorous plant. If a fly comes here, triggers there are this little. I forgot the scientific name, little sensor sticks that hang out and stick out over there. The fly comes in and disturbs those sensors. The thing goes whoosh, and the fly becomes lunch. So that was our motivation, that this effect is happening fast. But it turned out that we were extremely lucky, because this is one of the rare plants that actually has something that's called action potentials, which is something that's normally found in animals, not in plants. But here there are also action potentials, and we were able to actually detect this. And this is like an interesting direction, magnetism of plants. So just maybe to finish, I'll flesh out a few projects that are ongoing where we take part. So there is a project called MOQUABIS. By the way, I'm in the business of coming up with crazy acronyms for projects, and this is half of the success of a project. But I must tell you that the NV project by the name Envious didn't succeed. Okay, so but MOQUABIS did, and this is multi-scale quantum imaging for biological systems. It's led by Nicole Fabri from Florence. And the main goal here is actually biosensing of cardiac tissues in order to study these action potentials in the heart, which is of obvious interest. And in some of the sub-projects, people grow the heart cell structure on top of diamond and try to measure them as well. And they don't want to be microwaved, remember? In another project that is led by Angela Whitman at Mainz, which is called HIMS, Hybrid Chiral Molecular Magnetic Systems, where investigating the effect of chiral molecules on magnetism. And this is not obvious at all that chirality would affect, for example, magnetization of a sample underneath it, but it does. And this also is related to something that's called CIS, chiral-induced spin selectivity effect, and many other interesting things. And Diamond really comes in here, and Angela also does, in addition to working with us on this wide field imaging, etc. She's also involved now in scanning diamond magnetometry. We have another project. I had nothing to do with this acronym in this particular case. It was Arne who is leading the project. It's called Diagnosis Diamond-Based Quantum Sensing for Neurosurgery. And this is, I'm almost done. And this is to guide neurosurgeons during the operation on the head, typically cancer surgery. So can I have 30 more seconds or maybe 1 minute? Okay. So a few years back, so this comes to actually the application that where I spend personally most of my efforts on. It's fundamental physics. So a few years ago, my colleague Mariana Safronova called me up and said, look, there are so many wonderful quantum technologies, and they will result undoubtedly in the next 10 or 20 years in some amazing discoveries in fundamental physics. Why don't we invite our colleagues to describe different technologies and their applications? And so we became guest editors of Quantum Science and Technology. There are about 21 papers about different things. I think it was quite interesting. And then the journal asked us to write an editorial to introduce it. And then I wanted some catchy title, and so I proposed this title. And as always, we write a paper, and before sending it to the journal, we send it to the archive. So I should tell you, this is the one and only, maybe it will be more, but so far, one and only time in my career when my paper was rejected from the archive. And it is published in Quantum Science and Technology, but you won't find it on the archive. And I think that is because the curators expected some biophysics, and they didn't find biophysics there because, of course, it was about elephants in the room introduced by the previous speaker, the big problems in physics. For instance, dark matter is one of the biggest elephants in the room. And so, in summary, I told you about this really, really primitive magnetometry, nevertheless quite effective, and all possible kinds of applications to biology, rotation sensing, fundamental physics, etc. And I do not have time to really talk about this, but this is actually more related, I believe, to the subject of this meeting, and I'm really hoping to have some interesting conversation with Jamir, for example, specifically about this topic. It turns out that I'm sorry, too many buttons. That levitated magnets have amazing properties. For example, they seem to beat a standard quantum limit without any squeezing. And they also beat energy resolution limit. And what's happening there, and what are the reasons for this and what are the applications is a very interesting topic for a separate discussion. Thank you so much.